This is our Unit 11, Understanding Earth and our Geology.
Alrighty, peeps. So as we talked about before break, we looked at the geological time scale. So the geological time units is how we divide up our geological time. So it's not like, you know, our years and our decades or even our centuries that we kind of measure our time by. Geological time is on such a bigger scale. And when we think about like our lifetime in the grand scheme of geological time, it is like a speck of a time in there. And so we'll kind of take a look at that very briefly. We have already watched this video about geological time, but we would highly recommend you using that as kind of a good overview of where we will go in terms of the time span of time that we are looking at. So those GTUs, or those geological time units, you can see on the left of the screen, we have eon, era, period, and epoch. And so basically, it's kind of like our divisions, just like a century, a decade, a year, a month, a day. It's just another way in which we divide up time and how we label it. So an eon is the biggest, all right? And eons usually span billions, that's right, with a B, billions of years. An era is kind of like a medium level, all right? That's just hundreds of millions of years, you know, just like that little bit. And then a period is, again, a little bit smaller than that, super tiny, just about tens of millions of years. And then those epochs are they're just teeny tiny. I mean, that's just only roughly about 10 million years, a blip on the geological time scale. These couple of images on the right are kind of nice. And again, Googling generation that you are, you can Google geological time scale and get a lot of interesting images, infographics, stuff like that, that kind of takes you through the terms and things like that. Obviously, we're familiar with like Jurassic and Triassic from the movies and just dinosaurs were cool. But it's also good to know kind of where we are at now. So in terms of, you know, bigger picture, if we look here on the side, we have the Precambrian time. That was our first kind of eon, so that's very early on. Then we kind of make our way into the Phanerozoic. So that's the current eon we're in, but then we're going to kind of break that down and look at eras just because eon is so large. And so we have Paleozoic, we have Mesozoic. Mesozoic is where we had dinosaurs, Triassic, Triassic and Jurassic. And then lastly, we are in the Cenozoic era right now and currently in the Quaternary period. But more importantly, and on that tiniest level, we are currently in the Holocene epoch, because basically we are living in a time where we have people, humans, and so that is why we call this time frame that we are in the geological time span as being that. Why is it important that we kind of make our way through? Because the Earth is really old, all right? The Earth is roughly around 4.5, 4.6 billion years old, and again, billion with a B. This link here with this little asterisk takes you to the History Channel and gives you kind of a nice little, again, based on scientific evidence, a good hypothesis of kind of what the Earth looked like when it was forming and how that whole process took place. Very, very interesting. Lots of geological changes over time. And the question we normally get asked is, how do we know? Right? How do we know? We know that based on geological evidence. So we have different types of rocks and minerals that have been found, and they're pictured on the right-hand side, two of those, one from Northwest Canada and the other in Australia. One is a crystal, the other is a mineral rock, and those are pretty close to early Earth. We don't have anything from like the day you were born Earth, because it most likely was very molten and hot and everything melted. So we don't really have things until stuff started to cool off just a wee bit. And that's where we end up with like this Acasta mineral and then this zircon crystal that are pretty close to the age of the Earth. And so again, the question becomes, how do we actually calculate that? Well, back in the day, we used to do, and still do to a certain extent, utilize something called relative dating. And Ms. Case is going to talk pretty much for the rest of the time about that. And basically, we kind of take a look at different layers of geological rock and take a look at fossil placement in there, and we're able to determine relative age. So we don't have exact numbers or times with that, but we have a relative, like this was older than this, or this is newer than that. But more recently, we have been able to utilize radioactive elements, particularly the half-life decay of uranium, to be able to calculate ages of rocks and of our planet, as well as other places. And so we're able to measure those elements and their radioactive byproducts, and then be able to calculate using radiometric dating, which is something, again, relatively new. All right, and we talked a little bit about that in our nuclear system. So Ms. Case is going to talk about how we utilize relative dating as well.
All right, so relative dating comes from Nicholas Steno, and he utilized these laws in order to determine the order, like Ms. Laporte said, over the actual, in order to figure out that age. So I like to think of this first one, superposition. That means that the bottom layer of the rock formation is older than the layers above it. So it's similar to stacks of old newspapers or magazines. The other thing I like to think about is your laundry basket. The clothes that are on the bottom are the older ones that you've worn. Same with your garbage can, right? The stuff on the bottom of that garbage can is going to be older than the things you put on the top. So that is our way for superposition. So anything that's on the bottom layer is older than those formations that are on top of it. On these pictures down here, you can kind of see the different layers of the rock as it's going up. Good. Yes, perfect. So you can see Ms. Laporte there is pointing those out, those layers going across. You can see at what point what layers were embedded there. The next of Steno's laws is original horizontality. And that means that our sedimentary layers, or those rock layers, are initially deposited in horizontal layers and due to gravity. But any layers that are now folded, tilted, vertical, those were later altered based on those outside forces. So those are going to be your disruptions from natural or unnatural disruptions. So either earthquakes, maybe wind, erosion, anything like that. So you could see that down there on those pictures on the bottom from real life places there in Utah, actually. And then there's also some pictures up there at the top right, which definitely show you exactly what's happening in those real life photos there. Those photos are from some of the Mighty 5 national parks in southern Utah. And then we have Steno's law of lateral continuity. So here you'll see the rocks, the sediment extended laterally. So they were originally horizontal when they were formed. And as erosion has happened, you'll see some erosion happening there, but you'll still be able to see the layers going across even after that erosion has occurred. So those ones down there on the bottom, that is Bryce Canyon. So those are what are called hoodoos, and very beautiful place, but they are definitely little pointed areas where you can see that layer going all the way across. And same with that second and that third picture as well. So you can see those lines forming that go straight across from one part of the rock to the other.
And one of the best places to see lateral continuity is at the Grand Canyon. It's on my list. Case and I talk about traveling all the time. It's one place we haven't been to yet, but it is a geological, like, just wonderland of things. And so you can see the diagram on the left that kind of diagrams out what we're looking at on the right-hand side. You can see the Colorado River making its way through here. That is the disruption, if you will, that made the Grand Canyon as we see it over time, as well as a few other things. But you can see a lot of different pieces, not only of lateral continuity, but also superposition, right? Older layers on the bottom. You can see some original horizontality and that shifting that happened. But what's really nice is as you look across the Grand Canyon, so these layers that are on the left-hand side of the picture are going to align and match up with the ones on the right. So at those same levels, those are, again, laterally continuous. They match up as we go across. And that's really helpful for geologists when they are looking at fossil remains or they're measuring and looking at different minerals or compounds that are found there, because it provides them with evidence to be able to talk about relative ages of a lot of the things that they find in those locations.